and the session of the day. Now for the first talk of the morning, Luís Gustavo Mendes is going to talk about metamorphoses of a Lins Neto family of foliations and elliptic fibrations. So.
Thanks to organizer. I'm honored by the presence of former professors, teachers. I wait in Lins Neto. Where is Lins Neto? Let's start taking two circles, tangent, two horizontal lines, tangent to them, and then let's compactify to P2. Here is the line at infinity. Here, let's call L1, L minus 1, C1, C minus 1. Both circles intersect at infinity. Imaginary points here. And let us ask, as Lins Neto did, for degree 3 foliations tangent to such configuration. Let's call this C7, because the degree is 7, 2, 2, 2, 4, 6, 7. And the tangent divisor of degree 3 foliations has degree 7, so there are essentially a one-parameter family of foliations tangent to such configuration. Let's take generators of is a pencil of foliations. Let's take as generators the same as Lins Neto did at Asterisk and unpublished paper. I can give the reference. So let's take two forms defining foliations. Let's say this F0, this F infinity, and so this is something like this. Okay. This pencil of foliation. So what we observe is that there are in the family there are fixed singularities. Radial, 1 is the coefficient of linear parts, the Camacho-Sad 1 is a radial, 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 and these are 2, 1, that is linear part 2x dy minus x minus y dx, the critical after 2 blow-ups. This is fixed, fixed, fixed. And in blue, mobile singularities. These Camacho-Sad minus 4, minus 4, minus 2, they move as T changes. Okay? The other ones are fixed. So Lins Neto remarked very interesting things, like something like this. For T generic, let's take T special first. When T belongs to Qy, y is the imaginary, the foliation Ft is an elliptic pencil. But as you see, a pair of foliations of this family is completely transversal out of the configuration. So for T generic, Ft is turbulent. Is turbulent foliation relative to any elliptic pencil. What happens after blow-ups? The elliptic fibrations have singular fibers like this. Kodaira zero star, 3, Kodaira type 3 after blow-ups, Kodaira. And these singular fibers of the vibration obtained from the pencil, they have these shared for all vibrations, these non-central elements. But the central element depends on the parameter here. And for generic parameter, this is not invariant. And the foliation for generic T is a turbulent foliation relatively to the elliptic vibrations that are here. So, Lins Netos remarked that F1 is a pencil of cubics generated by one circle and one line, one circle and one line. That F infinity is a pencil of quartics, of elliptic quartics, that is quartics with two nodes at the imaginary points there. And remarked that for T in the set, there are coalescences of singularities, just for the set. For example, this mobile comes here and become a singularity of the pencil generated by this circle in this line and this circle in this line. So there are few coalescence cases. The rest is the singular types are exactly what you see. 2-1, the critical after one blow up, radial, the critical, and singularities with negative Camacho-Sad and linear part. Pardon? Pardon?
Between the two circles, the tangent point.
Here, yes. 2-1 also, yeah, I forgot. 2-1 type, okay? Okay. So, natural questions are natural. Lins Netos also remarked that the degree of the elements of the elliptic pencils is unbounded as T moves. This grows without bound. So, but he analyzed just a few cases. The question is, for T belonging to Qy, what is the degree of the pencil as a function of T? For example, here, degree 3, for 1, degree 3, for infinite, degree 4, etc. The degree of foliation is the same, 3. But the elements of different pencils have different degrees. So the question is the degree. And the second natural question is how to produce all pencils, the generators of all pencils. Então, effectively produce the generators of all pencils for all T belonging to Qy. For the pencil of quartics, the generators are the two circles. One is two circles, the other one is this line, and this line to the square. So, okay, for the first question, our answer is, I forgot to say that is a joint work at Adolfo Guillot and Liliana Puchuri. Without them, I could not make the work. So the first theorem is, for T different of 1, because T1 we know is a pencil of cubics, consider the following expression. gamma t equal y, t plus 1 over t minus 1, and t belonging to qy. And here, write this number in qi as a quotient c plus dy a plus by, a, b, c, d integers. Write this with relatively prime, okay? Then the degree is 2 I also, yes. This is the formula, theorem 1. And the metamorphoses in the title is to explain the role of this map, connecting equations in P2 with equations in other surface. And theorem 2 is that using the automorphism, let's write Tz in the projective plane, that linear automorphism that sends z to minus z, Tx that send x to minus x, linear automorphism, using one Cremona quadratic and one Cremona quartic, we generate all pencils starting with anyone, starting from, let's say, F1. So this is recent. I thank the contribution of Adolfo, because I had obtained with more Cremona transformations, and just for zy, zy, and then now for all t belongs to qy. So the first part of the conference will explain the geometrical role of this. The second part will talk about Cremona symmetries and linear symmetries of the family and how they change, not the degree of foliation, but the degree of the pencil, of the elements of the pencils. Okay? So let's recall simple notions for takeoff the plane. X, y, z goes to x, y minus z. X, y, z in the plane, in the homogeneous coordinates, send to minus x, just linear. And this one, these are Cremona. These are not linear automorphisms, they are symmetries, Cremona symmetries. So let's take off from the plane. For this, let me recall the notion, well known in algebraic geometry. That's the notion of branched covering. I just will remark some little things locally, and then after we go globally, okay? The idea is to try to get a morphism from one surface to another that is 2 to 1, except on a certain curve, or branching curve. And the idea is the following. You take a divisor, an even divisor of a surface. Even divisor means that the line bundle associated is a product of line bundle, a square of a line bundle, okay? So these conditions, global condition, enables us to give sense to such a, let's omega y be a section, local section here of L, And you can take this operation where Fy is the equation of D, is a local equation of D, have several local equations. This equation is a two-covering, ramified, branched on Fy equals 0. But for having a global sense, you have to have these conditions because when you use this as section of L, you get, for example, in Y inter J, you get, for example, this is the cocycle of the line bundle, J. And here you can write phi Ej square, thanks of this, because this is a section of D, Fj. So you can cut, and you get omega j square equal Fj square. So has a global sense as analytical set in the total space of L. So this is condition. So even, to be even in the plane is just to have even degree. But in other surface is not a trivial question. When some divisor is even. Let us see in the example. Another question, local question, is that singularities of this, so here is x, y, here is another variety, so this is a surface in 3 space. Singularities depend on singularities of this. So imagine you have a candidate to branch cover that is singular, like this. Then the object, the ramified, the branched cover surface will be singular. In order to not have this, we can separate this, candidate a branch covering. In here, you have now, here you want to branch on this. Here you arrive to branch on this. And this object cuts, this is a P1, cuts in two points, so you become another P1 in the double covering, and for a smooth double covering. And when you have tachinode, like there, you have two first blow up, and then second one, let's put in colors. Let's put a color here. This is the branch, and here you want this as a branch. So they come here, after they come here. And this A1 will become is a -1 curve. Here becomes -2 curve. And this will be duplicated. So this is E2. This will be duplicated. This one will be a branched P1 over the A1 P1. And so you have to duplicate this and to branch P1. So you have two copies. We will have two copies of -2 curve. This curve will be a P1 branched, and this will be the branch curve of the two covering. Let's see this globally. So what will you do? We will desingularize before taking the double covering. So let's explain here. I will take the candidate is this degree 6 curve, 2 circles and 2 lines, it has degree 6, not 7. Then I desingularize, so you see here -1, the critical radial. Here we had a radial point, so this is the critical, the critical, the critical. Here we have the desingularization of the tachinodes, of the contact points, so we have a -2 exceptional, here as a -1 radial, etc. So you see all the elements. There are 13 blow-ups. The family of Lins Netos foliations is equireducible, so 13 blow-ups are enough to reduce the singularities. And then, after this reduction of singularities, let's branch over this curve, and red, orange, magenta, and green. These will be our branch. So Let's take the branch. Voila. Here you have each radial point becomes a P1 double covering another P1. Here you have two copies. And here you have a P1 branched. This means branched is a regular curve, but I try to say that this branch covering ramified on the red and orange. So you have different curves. And what's nice is that this surface is a K3 surface. The canonical divisor, let us think about an elliptic curve ramifying over P1. Elliptic curves have canonical trivial. So this is this dimension 2 analog. This is a surface with canonical trivial, recovering 2 to 1 the plane, branched over an even degree divisor, which was the singularized. Okay? So you have two copies of line of infinity because it was not of the branch curve. You have some copies of exceptional of -2 curves, etc. Also is nice that all dotted curves are -2 curves. Any P1 in a K3 surface is a -2 curve thanks to the genus formula. So you have -2 curve, -2 dotted curve, -2 dot, etc. Okay, this is the first smooth branched two covering. Let's take another branched cover. Well, the problem is that in order to take a branch cover, you have to find an even divisor. Okay, excuse me. You have to. So, by a result of Nicolin on a K3 surface, 16 disjoint -2 curves are the support of an even divisor. It's a very clean criterion, even divisor. This is a result of Nicolin. Excuse me. So let's find the even divisor here. The even divisor will be the two copies of L infinity, the colored curves, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 -2 disjoint curves. So let's branch over the divisor made by colored curves, two copies of infinity, and these two copies of invariant P1. Remark they are all invariant P1. And then let's take another smooth covering. And you have now, attention, here, look, this P1 passed by 4 branches of the 4 local branches of the branching curve. So in the next figure, it becomes an elliptic curve. This is an elliptic curve with 4 branching points over a P1. So you have now elliptic curves here, 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 and the rest was used for the ramified double covering, but you have now elliptic curve. I assert that this surface has canonical class located at 16 -1 curves. The -1 curves are these two black, the colored, these ones, the invariants. You can find here, by the same idea, 16 -1 curves where the canonical class of this surface is located. I don't know if you can say this. Let's contract such 16 -1 curves to get an abelian surface. So here you have a product of 2 elliptic curves. there are 16 points in this figure. I apologize for the quality of the drawing. But these 16 points are the contraction of 16 curves. The elliptic curve, Lins Netos already had shown. The elliptic curve is the quotient of C by the lattice 1y, the square lattice. This was remarked by Lins Netos. And this is an abelian, special abelian surface of product type. And here, if you remember that the mobile singularities had linear part with Camacho Sad 2, after 1, negative, and after become -2, after become -1, and are contract. This here, in this surface, we have from any foliations of Lins Netos family, a regular foliation. A pencil of regular foliations here, and we can use some known facts to show that Lins Netos family have become, here we have T, here we have the rational 2-to-1 map, and here we have a smooth family of, a pencil of foliations of type dv minus alpha du equals 0, where uv are coordinates of E times E, or C times C, or passing under the quotient. So all becomes completely smooth and linear. Here we have a situation very much resembling very much the classical case of R2 and the linear foliations. When you pass to the quotient to the torus, these linear lines becomes either closed, either non-closed curves. This was one of the first theorems that I liked in the theory of foliation, dynamical system, Denjoy. It's the same, it's analogous to the same. Here you have linear foliations coming from the family. I assert that this alpha is gamma t of the theorem. This is alpha. In order to see this, it's important to consider the coalescent case. For example, in t equal 1, this is a generator of the pencil of cubics. This is another generator. You have here coalescent singularities. And you can, this will be, in my notation, is E5, E4, the first blow up, and then E5. E5 now is invariant, and here another. So let's see where is E5. E5 is here, E5. So this dotted, in general not invariant, becomes invariant for t equal 1. So t equal 1 is sending the vertical foliations. Vertical foliations is when alpha, when alpha is infinite. Alpha belongs to P1. Alpha infinite is du equals 0, is vertical. So you see 1 is sent to infinity. You have a Möbius map from the pencil of Lins Netos to the pencil of a linear pencil. And this Möbius you can determine using some values like T1 goes to infinity. So the form is this. T equal 1 goes to infinity here. So, okay. In particular, before the particular, now we can control the ramifying double covering. We can control, you can use projection formula. We can use a formula for intersections on abelian surface of curves on abelian surface of Hayashida-Nishi, and we can get the degree. This is speciality of Liliana to compute such control, such coverings and projection formula and Hayashida-Nishi to prove the degree. So let us start now from above. And let us consider that to generate the elliptic pencils here is essentially in the abelian surface to send any, slope alpha is a slope belonging to Qi, to send it to the slope 0, for example, slope vertical. So here we have the certain, this automorphism of here are, you can consider the PGL2ZY. This is the rotational part of automorphism, and semi-direct product with translational elements that we can prove to be Z2 times Z2. So these are the automorphisms that pass to the quotient for a diagonal action like this of order 4. I came from down to up now in the other sense. This is a quotient of order 4. And these automorphisms are those that pass to the plane. And then using, as suggested by Adolfo, using Frick-Klein and using results, classical results by Frick-Klein and van der Waerden, we could try to find the Cremona that produce such automorphism, generate this group of automorphism. So let's show, here we can put coordinates in all the abelian surface because we know the non-trivial isotropy points under such action are the 16 points. You can put coordinates, half periods, one half, y over 2, 1/2 plus y over 2 are the half periods. So we can now also put coordinates. We can lift the symmetries. We can do all we want. Here, these are the linear symmetries or Cremona symmetries that lift and generate this group. So we can send any slope to the slope 0, so you can effectively produce. What about, about Cremona symmetries? Let me give you the most basic example. This is a well-known standard Cremona transformation with base points at line infinity and 0, 0, 1. So you see by the colors, the non-trivial movement, which is done by Q. And Q is preserved the arrangement of lines, of curves and circles, and preserves the family of foliations. In general, changing the parameter. Let me, excuse me. CR2, CR4, they change the parameters. TZ send FT to FT. TX send FT to F minus T. These two changes a lot, the parameters. But let us come here. Q is incredible. Q preserves each foliation, Q. Not just Q, also TZ composed with Q, that is Q composed with TZ. And here we have, with identity, the elements of Z2 times Z2. So these transformations become translational in the abelian surface. Huh? But, the result theorem 2 is complicated, depends on algorithm, depends on Euclidean division, etc. But I will focus in this transformation, this Q. Because as a former student of Lins Neto, of course, comes to my mind the natural question of take the quotient by Q. Q is in the plane, is a Cremona map. Well, Lins Neto is here? No? It's natural. So we are very happy with this, but what happens if I take the quotient of the family foliation by Q? It must simplify the family. Maybe producing a family of Riccati foliation, I don't know. But I was really interested in this. So let me show you a metamorphosis in the opposite direction. We start from the plane, we pass to an intermediary surface, after to a abelian surface. Now let's start in the plane and let's go down. I expect it will be a surprise. Here we have P2. Here we have an evolutive, so it's a group, produce a group. Key is evolutive. We want to quotient Ft and the plane by Q. We know that a finite quotient of P2 is again a rational surface, but what happened with the foliation? To describe this quotient, we do the following. P2, Q has 4 fixed points. So when we pass to the quotient, we can take cubics invariant by Q and embed this in P3 as a Cayley nodal cubic, 4 nodal cubic. Something like this in P3. Here. This has 4 A1 singularities. A1 singularities corresponding to each fixed point of Q. So you can take a Cremona space transformation based on these 4 points. Is the standard Cremona cubic transformation, and this goes to the plane. Okay? So we embed the quotient as a singular cubic surface, then we desingularize the surface by a Cremona space cubic transformation. And here, P2, we can now play with trying to find foliations, let's see HS, that under this quotient map, rational map, let's call pi, is a rational 2-to-1 rational map, pi. We can find, try to find the foliations in P2 such that the pullback is the Lins Neto family. This is a kind of a linear problem. We can find the family. So let's start, for example, with F1, the pencil of cubics. Here there are the generator blue, the generator red, another generating green is a double line and the line at infinity. Let's pass to the quotient. And in the quotient, we have a family of degree 4 foliations, not 3. And a configuration of conics in blue. Here seems not connected, but are connected. In blue, in line, in red, and the conic, and a set of green lines. This configuration now is invariant for all HS that are degree 4 foliations, not degree 3, degree 4. Here are degree 4, while here are degree 3 as foliations. Okay? But I start working with trial and error and obsessively working, and I start finding that HS is birational equivalent to the Lins Neto foliation. Strange. This is birational equivalent, again, with FT. Maybe ST, so we have to take care of the parameters, but here is a 2-to-1 map. 2-to-1 rational map, I take the quotient, and then I find a birational map, a 1-to-1. So I almost become crazy. I cut a foliation by its symmetries, a group of symmetries, and I find the same foliation. We have a lot of examples for Hilbert and others. When you cut by the symmetries, the quotient is not birational equivalent. So I start thinking I was crazy. Huh? Let's explain what happened. Let's explain what happened. So here we have F1. In order to explain, I will take the intermediary surface, the K3 surface. Here, Lins Neto observed that all the foliations in the pencil have two fibers of Kodaira type 3 after blow-ups, after not minimal, I0 star. But we remarked that when we took, here is the blow-up plane, okay? All the fibrations are here. This one depends on T, but the horizontal do not depend on T. What I remarked with surprise is that the first ramified cover produce what is called quadratic base change in the fibration. This fibration is duplicated, this singular fiber, excuse me, is duplicated, but these one, they are changed in the following way. This component, which is common to all fibrations, become 2 copies here. This component becomes 2 copies here. And now we have 4 I0 star fibers. Okay? So let us regard in this K3 surface with 4 I0 star, that is a kind of let's say, improve this vibration. This is a rational surface. This is a K3 surface. Let's look the effect of Q. Q, the strange symmetry that I took. Let us lift here to this surface, and let's see what happened. So when you lift to the K3 here and left this part, you can follow the effect of Q because you know how it lifts in the abelian surface. And we see that it interchanges Q, the lift of Q, interchanges this horizontal, and as an evolution of a P1 has 2 fixed points. The same here, the 2 fixed points is an evolution. Interchange yes, 2 fixed. So the lift of Q has exactly 8 fixed points, exactly 8 fixed points. A result by Nicolin says that an evolution of a K3 surface with exactly 8 fixed points is symplectic. Is symplectic, preserves the global 2 form. And the quotient is another K3. In our case, we have more. Q preserves F1 because it preserves any foliation in Lins Netos family, but more, it preserves each fiber of the fibration F1. Each fiber is preserved. And the Mordell-Weil group of this, excuse me, oh, this is a rational. This is the rational surface. Let's pass to the K3. Here, the Mordell-Weil group by a result of Akuata is Z2 times Z2, the Mordell-Weil. That is the group generated by sections. You can take a zero section. You can take, excuse me. You can take a zero section. You can take another section of this group of sections. And this is order 2. And we can make computations to see that the lift of Q is acts exactly as this order 2 section on the elliptic fibration. When you have order 2 section of an elliptic fibration of a K3 surface, you have Van Gemmen-Sarti involution, which is symplectic, which is symplectic, also Nicolin is called. So, a Van Gemmen-Sarti involution is produced by a order 2 section in the group of sections. It is the same effect of Q on the generic fiber, Sarti involution. And the Van Gemmen-Sarti involution are examples of Nicolin. So here, I'm almost finishing. Here, let's take the quotient by Q is a 2-1 map. The fixed point becomes singularities in green. The black becomes 1, 2 blacks become 1. Here we desingularize and reappear the green curves. The black ones have 1 copy. When you look to this map, is a 2-to-1 map, branched over this even 8. These are a set of even in green. Even 8 is 8 curves that are an even divisor because they are the branch curves of this map. And this map produce what the physicians, Malmendier, Klinger, and others in the string theory, etc., calls a duality of K3 fiber surface. And the map is a 2 isogeny. Is a fiber-wise, the map, the 2-to-1 map that you see there, is a fiber-wise 2 isogeny of the elliptic curve. This is an endomorphism of the elliptic curve, but between isomorphic curves. The curve is the same, is the elliptic curve of all the talk, but the map is 2-to-1. So think about a P1 recovering 2-to-1, another P1. It's possible to have isomorphic curves in a 2-to-1 map. So this was the light that I searched, and these in physics are studied by, for example, Malmendier, lot of papers in algebraic geometry and physics and mathematical physics, and Klinger, Doran, and others. So they know very well such a transformation. I didn't know, so I was pretty scared about this. So there are other metamorphoses, but I have no time. I can make a metamorphosis from Lins Netos to Kondo's models. Kondo has models for K3 surface as branch covers of P1 type P1s. I could make a metamorphosis. Adolfo has made another metamorphosis to commuting polynomial degree 3 vector fields of C3 the Lins Neto family becomes commuting polynomials, which is rare, which is difficult to find. So it was a pleasure to study such things. Thanks to Lins Neto that is here.